Good day, my name is Franzua van Heever, and this is my EAL3601 Alternative Energy Design project. The following project presentation will overlook. Good day, my name is Franzua van Heever, and this is my EAL3601 Alternative Energy Design project. The following presentation will feature the alternative energy design of a rural hospital in Kwakwa. An overview of the following presentation will contain the topics Introduction, Objectives, Delimitation, Research and Background, User Requirement Specifications, Design and Methodology, Project Costing and References. Introduction. The project aims to design an alternative energy-based energy system for a rural hospital in South Africa. The layout of the hospital is provided by UNISA, and UNISA will be considered the client in this regard. The project specifications are provided under the EAL3601 module resources. So the project specifications were taken from the MyUNISA site and referenced accordingly, and those specifications were adapted to fit the project descriptions and outcomes. The project has the following objectives. The first objective, research applicable areas of alternative energies as a foundation to the project. Without prior research, nothing can be designed factually. Objective number 2, design an alternative energy off-grid power system that can provide power to a rural hospital in South Africa. The project requires that the energy source of the design should be alternative energy, and whichever type it may be, the project also suggests that it should be preferably it should be a solar energy design. Using the exact source power requirements, size the system and establish the required kilowatt-hour capacity for the hospital's power plant such that it meets the established requirement. So the system needs to be compatible with the hospital and the electrical system demands of the hospital in question. Then also draw a detailed layout of the design. This is the CAD component, so that if the design should be implemented, the contractors may know where to place what and what the specifications and standards are that will be adhered to. Compile the design, CAD drawings, single line diagrams, calculations, etc. into a final report. So all of the components, finally research, design, methodology and user requirements will be compiled into an academic report. After the project completion, review the report and reflect on whether the set objectives and desired outcomes were reached. Also provide possible improvements and shortcomings to the final design. So after the project was designed, in the academic report, all of the outcomes are evaluated and it is established whether the objectives and user requirement specifications were reached. Project delimitation. This section focuses on what will not be done in the project. So what are the limits of the project in terms of what will be provided and what will not be realized within the project. The following points will not be addressed or done in the project. So the first delimitation point is the project will not be installed or built as a prototype. And secondly, some of the construction features will not be included in the costing of the project. So this is simply a theoretical project. It's an academic project, so it does not have to be implemented in an actual location or rural hospital. And secondly, the construction of the project in terms of building materials and construction layout and scale of construction is not going to be completely addressed in terms of costing and specifications. Research and background. Before the project design commenced, various points of interest to the project were researched to establish a foundation for the project design. The first most important part of the research was a look into alternative energies, of which the first is solar energy. So solar energy is a renewable type of energy that consists of using solar PV panels to harvest energy from the sun and that energy, light energy, is then turned into electrical energy via solar PV panels. The next source of energy is wind energy. Wind energy uses wind turbines, and it turns wind stream energy through mechanical energy into electrical energy. Next, we have geothermal energy. Geothermal energy is a type of energy source that uses thermal energy from the Earth's inner core to generate electricity. Then we have hydropower. So hydropower can be either run off river or it can be reservoir based. And hydropower is using gravity built dams and reservoirs to use water flow in order to generate electricity. Ocean energy is a form of energy that uses underwater turbines and utilizes the currents in the subsea ocean area to generate electricity. This is still a very new form of alternative energy, and further details can be found within the project report. Bioenergy is a type of alternative energy that uses biomass, and biomass is then turned into heat energy, and this is converted to electrical energy. Solar PV for hospitals in Ghana. One of the topics that were looked into was an article about implementing solar PV for hospitals in Ghana. The following points were addressed. First of all, it was found in this article that solar implementations in Ghana that were already successfully done can run critical systems continuously. So in other words, there's a backup. If there's a power outage, then solar PV can successfully run critical systems such as life support and ICU-based machines. It's a lower cost solution than a generator-based system, so a fossil fuel generator was found to be more expensive than solar PV. And one of the other parts that this article investigated would be organic PV panels, OPV panels. This is still a new development. However, organic PV panels are much more friendly to the environment and can then be used in solar installations. It was also found in this article that organic PV panels can even be more efficient than poly or monocrystalline panels, the conventional panels that we are using today. And this is still a point that will need to be further researched. And then hydropower was also looked into as a possible solution, since it is a very effective form of alternative energy. So consider small-scale hydro power plant as a possible solution. The particular plant that was looked into is called a run-off-river type of plant, and it looks like this. So a run-off-river plant is not a reservoir-based plant. It is a dynamic plant, so you do not need to store water and then release the energy when it's required, like with a dam project, a hydro dam project. The run-off-river project looks like this. It has an intake upstream, and then there is a canal and a penstock. The penstock takes the water downstream, and then at this point, due to gravity, the water flow has established enough energy to rotate a turbine in the powerhouse, and that turbine then generates electricity through a generator, and that can then power a house or a rural community or a rural hospital in our case. So consider small-scale hydropower plant as a possible solution. The particular study and references to this study is the Kwamadiba small-scale hydropower plant on the Tina Falls area in the Eastern Cape. The small-scale hydropower plant can be more feasible financially than a grid connection to a rural area. What this means is that in some cases, extending the existing grid to a rural area is more expensive than just simply implementing a small-scale hydropower plant, such as a run-off-river type plant. Solar PV will be used since there is no guarantee of a viable river source near the hospital. So the reason for choosing solar for this project, ultimately in the end, solar PV was chosen, is just simply because there was no specification provided that there is in fact a viable source of water or river flow near the rural hospital that's being designed for. but we do know that there are good sun hours in South Africa, and particularly in the Eastern Cape. So solar would be a viable option. So types of solar PV systems were also considered. Types of topologies were investigated. Grid-tied, off-grid, and hybrid. So a grid-tied system is a system that usually does not feature battery backup. So it's simply a system that during the day you can directly use solar from the PV panels, and any excess power generated can, in some cases, it's not always the case, but can be exported back onto the grid. And then the user or the person owning the solar plant is then reimbursed for this power that is exported back onto the grid. This is called grid exporting. So a grid-tied system is a very economical system and can greatly reduce the electricity bill. The next type of system is an off-grid system. This is a fantastic system if there is no power from the grid available. And this particular project is an off-grid system because we do not know what the condition is, if there is any grid provided to this hospital. So the aim of the project was to design a completely off-grid system that can provide a full-scale solution 24 hours a day. A hybrid system is a combination of a grid-tied and off-grid system. So off-grid system will usually feature battery storage or generator backup, so that in the nighttime, or if we have rainy days, there will still be power provided, so that if there's no solar power from the panels, there will still be a backup source of power. The hybrid system will usually have a grid tie incorporated with an automatic transfer switch and can be switched between the grid and the solar, or even battery backup also. The user requirement specifications of the project. So these specifications were basically compiled from the requirements provided by UNISA, by the EAL3601 module content, and also considerations were made just towards the practical requirement of the project and what needed to be done. There are 10 user requirement specifications, and there are further details on them in the report. So design a complete electrical system source to load for a rural hospital in the Eastern Cape that is based on an alternative energy solution. So the project must use some form of alternative energy. The medical facility and warehouse section should have their own separate three-phase power supplies. So the warehouse must have its own distribution board and its own dedicated three-phase power supply, which we will look at in a moment on the electrical drawing. The intensive care unit, ICU, should have a constant power supply with redundancy to ensure no downtime. So the ICU is considered a critical systems area, and we always want the life support machines to be functioning and on. So the ICU was prioritized in terms of generator backup and battery storage in the case of this project. Consider all necessary safety precautions to ensure that the design meets the required certification. So the SANS standards were used in this project and investigated to a certain extent to ensure that at least a single line diagram and the layout and placement of fuses and safety junction boxes were in the right location, and that the system would adhere to national standards in South Africa. The COC certification is a certificate of compliance. This was not done for this particular project, but if the project were to be implemented, a COC needs to be written out for the project to certify the project as being a legal electrical installation in South Africa. Load voltage may not deviate at the load, 6% for single phase and 8% for three phase. So basically we do not want a massive surge or deviation in power. The project needs to provide stable power from source to load. Single wall sockets should not exceed 4 kilowatts, so we do not want to overload one breaker. We do not want to dedicate one single breaker for too many sockets that can be used and then cause unnecessary problems like heating and maybe even a fire risk due to overcurrent. All sockets should be tied to earth leakage except for critical loads. So earthing needs to be implemented, and earth points are indicated on the project, basically to indicate where the DB boards are earthed. So all of this is done according to South African standards. Metal light fittings should be earthed, so we need to use essentially for single phase circuits we use 3-core wire, and then basically all of these metal lights are earthed to their from their chassis to the actual earthing point, going from the DB board into physical earth. This is done to ensure safety from electrical shocks, since the metal chassis of the metal light sockets are conductive. All sockets should be tied to earth leakage except for critical loads. So sockets the same will apply, 3-core wiring, and also down to through the DB board down to earth. And critical socket outlets should have their own individual circuit breakers. So the ICU was prioritized in terms of having its own dedicated circuit breakers, and as I said, battery backup and redundancy with the generator also. Alright, design and methodology. So this is the full electrical drawing. Please refer to the report and annexures in the report to review the electrical drawing. But this is the overview of the electrical drawing. It indicates the arrays of ground-mounted solar panels. That's on the top. And then we have a power room that was added to the hospital as it was given before. And then basically all of the electrical layout is shown throughout the hospital the way it's prioritized and planned. This is just a quick overview of the solar array. So basically what we have over here is we have two sections of panels, and we have them arranged in a particular configuration. So they are arranged as 5 strings of 13 panels per string. And the reason why this was done is to accommodate the specifications of our inverter, and that will also be given through in the report. So we have 5 strings of 13 panels in each string. So a string refers to one parallel branch. So we have 5 of those branches, and in the next array there are 2 arrays. The next array is also 5 strings, 13 panels in a string, and they are the Yinko solar panels as they were specified in the project report. So we can also see that each of our 2 arrays are 36 kilowatts in capacity. Then we have the power room. This was added in because I did not want to utilize the warehouse space for placement of the generators and all of the solar equipment and distribution boards. So we have in the top right section, we have a generator with its own dedicated earth. Then to the right of the generator, we have the 2 lithium battery boxes containing the lithium batteries, the battery backup. Then on the wall to the right side, we have 2 inverters. Those are our 2 3-phase inverters, and they power 2 dedicated DB boards, one for the warehouse and one for the hospital. And also the earthing is indicated over here. We can see at the top left of the picture there's a DC combiner box B. There are 2 of those, so each of the solar arrays will have a combiner box, and also all of the DC fuses and DC disconnects are also placed in that area. This is the single line diagram of the project. This gives a way better description than the electrical drawing just of the solar PV layout and signal flow. So we have the Yinko PV array, and as we can see we have 5 strings of 13 panels each. And then we have a DC combiner box. After the DC combiner box, there is a DC disconnect. This is a safety feature that is implemented. And after the DC disconnect, we go into the 3-phase inverters, the 30 kilowatt inverters. The one on top, inverter A, will have battery backup and the 15 kVA generator with its own dedicated automatic transfer switch. So if the generator is required to take over the power, let's say that we do not have enough solar storage available. This particular system was designed with only 1 day of autonomy because that was done to save costs. So the generator will then take over on days that solar power has run out. The technical specifications of the project, so system size. Now in the report, this is way more detailed and all the calculations are shown. These are just the basic specifications. The final system size is 72 kilowatt solar PV array. This is based on the PV panel capacity. The system size, the ICU specification is that each ICU machine is catered for above the specified 250 watts. So there is more than 250 watts available, but that was the specified amount for each ICU bed. And there are 4 of those. The total required kilowatt hour per day is 331 kilowatt hour. That is the total per day, so it's not an instantaneous amount. The generator requirement is 13 kVA. A 15 kVA generator is specified, and total battery capacity is 2120 ampere hour. So that's 1 day of autonomy was taken into account. The project costs. So the total project cost came to 1.874 million. So 1,874,583 rand and 52 cents. We can also see it here. That is including VAT. So the cost without profit, 1,441,987 rand 32 cents. That's VAT included, and then 30% profit was added to for the design. And that is 432,596 rand 20 cents, and the total cost to client is 1.8 million, just over 1.8 million then, including VAT. That is the end of the presentation. Any further details can be found in the project report and its annexures. The references will now follow that were used for this presentation, as well as the project report. Thank you very much for your time.